Hi, it's Dave. Welcome. Today I'm joined by James Douma again, and we are going to dive into Tesla's latest Dojo Whitepaper that Tesla announced and Elon also commented on. James, welcome back on the show. How are you doing?
I'm doing great. It's great to be back.
Fantastic. Yeah, I noticed your tweet thread on Twitter about the Tesla Dojo Whitepaper, and Elon Musk liked one of your tweets. I thought that was pretty cool.
I'm glad he didn't reply to it. So once Karen told me that he liked one of the tweets, I'm like, oh God, like Twitter's gonna be useless for 2 days now.
Your
But he didn't,
notifications
so
just
I'm
blew up,
okay.
right?
Yeah. Yeah.
I hear you. So I want to go through this white paper together with you and talk about kind of what the white paper is about and why it's important. And a lot of people listening are going to be lay people who don't understand the technicalities, but might be interested in the larger implications, right? So I was thinking as an outline, we could just go through your tweet thread. I'll go ahead and link to your tweet thread in the video description, but I think this gives us some good talking points. This first tweet, you say that Tesla has released a white paper describing new numerical formats being used in Dojo. These novel numerical formats are created with the need of neural network training in mind. Then you say common numerical formats in current use have shortcomings that make their use in the training of neural networks more complex and less efficient that could be ideally achieved. All right, so let's unpack this a little bit. So when you talk about numerical formats, can you kind of give the audience kind of a high level overview of why do we need numerical formats, right? And what's their role in computing, but how is it different when you do neural network training?
Yeah, so a numerical format is the way that you represent a number inside a computer's memory or when you're doing a calculation. So computers are binary, so everything is ones and zeros. And when you store a number in memory, you have a certain number of ones or zeros to work with. And when you do the calculation, you're working with a certain number of ones and zeros. So a certain number of ones and zeros in a format, they can only represent a certain set of, they can only represent so many numbers. If you have 8 bits, there's only 2 to the 8 or 256 different numbers you can represent. And what the format says is for each one of those codes, what number does it represent? So that's essentially what a numerical format is. So the numerical formats that are in common use today, there's 2 broad categories. And one of them is just whole numbers, which go from like 1, 2, 3, 4, 5 up to some number, and where the biggest number you can represent depends on how many bits you have. And then another kind, which is like decimal numbers, like for scientific calculations, where you have 1.2345 times 10 to the 6th or something like that. So those are floating point, that kind, and the integer formats they're called integer formats. And it turns out that neither one of these is actually a really good fit for what you want to do in neural networks. In neural networks, you're typically dealing with really big blocks of numbers in calculations. They're basically matrix operations. And a matrix frequently doesn't have a lot of dynamic range in the numbers that are embedded in the matrix. This is just a characteristic of neural networks. It's not strictly true for all matrices, but for the matrices that are used in neural networks, this tends to be the case, where you don't need a lot of dynamic range within them. But between different matrices, you can have really big differences. Like the numbers in one matrix could be a million or a billion times larger than the numbers in another matrix, but the numbers in any individual matrix, they don't vary a lot. So if you want enough dynamic range that your number can represent any number in any matrix, you end up basically having to make really big numerical formats. But when you're actually doing the calculation, like when you're multiplying the matrix, you don't actually need a lot of bits. In fact, it turns out that you only need like 4 or 5 bits for the individual number representation. So if you only need 4 or 5, but the computer architecture you have is making you use 32, well, you're wasting all of this. You've got all of this stuff that you're doing, which actually isn't making your result any better. So you can imagine that if you built a computer that just used the 4 or 5 or 8 bits or whatever that you need, that for the same number of transistors or the same amount of memory, you get a lot more performance and a lot more efficiency, and you can store more stuff in memory and so on. So a numerical format that's well suited to neural networks would leverage the ability of a machine to do neural networks well.
Mm-hmm. Interesting. So, okay, so you say CFP8 and CFP16 address many of the shortcomings of existing formats and allow for 2x to 4x increase in performance and capacity of training hardware with improvements in hardware size, cost, complexity, and efficiency. So, okay, so let's unpack this a bit. So what is Tesla doing with these new floating point, protocols, I guess CFP8 and CFP16? What are they doing that's going to achieve such dramatic, let's say, performance increases over the past legacy of floating point formats?
So there's having a numerical format that's optimized for what you're doing has, like, broadly speaking, two advantages. One of them is that when you read and write it from memory and store it in memory, it takes no more memory and no more bandwidth than is really needed for the representational performance of the calculation that you need to do. And then the other is that having something which is well suited can mean that the calculation, like if you have a multiplier, a circuit which multiplies two numbers, it doesn't end up being any bigger than it needs to be to produce the results you want. So there's kind of this computational advantage, and then there's a storage advantage. And part of the storage advantage is how much memory you need, but the bigger for neural networks thing is how much do you have to read and write to memory? Because in neural networks, you frequently are writing a lot of stuff to memory and reading a lot of stuff from memory. And the current state for computer chip development is that that what happens on a chip is much faster and much more power efficient than any time you have to go off chip. So the off chip, there's this kind of memory bottleneck that you have. Like anytime you have to go off of your chip and like go to DRAM, or you have to go from one chip to another chip, and you have to transfer this number, it takes a certain amount of time, and that time is proportional to the number of bits that you're writing to the other chip or out to memory to do that transfer. And so if you have a numerical format that's, say, 4 times smaller than another numerical format, it takes 4 times less time to write a block of numbers to memory with that appropriate format. And that's essentially what we have here. Is Tesla has they have a 16-bit format and an 8-bit format. And these formats are largely replacing computations that today on more conventional computers are done with 16-bit and 32-bit numerical representations.
Got it. So they're basically taking the larger numerical formats, 16, 32-bit of the legacy numerical formats, and shrinking them down to 8 and 16-bit.
Right.
What are they doing? Is it? I know probably I'm not wanting to go into the weeds of the technicalities, but with broad strokes, can you kind of give us an idea of what Tesla is doing to achieve, those type of efficiencies or bring them down to smaller sizes?
So the format itself, so numerical formats, they have a floating point numerical format has 2 parts. It has an exponent, which basically says where the decimal point goes. And then it has a mantissa, which is basically the digit. So 1.234 has 4 digits of precision, and it has a decimal point after the first digit, right? So a floating point format has another thing. It has one thing that tells you does the decimal point go after the first digit, the second digit, the third digit? It's like times 10 to the whatever power. Where the power thing, that's why it's called the exponent. Although for binary numbers, it's 2 to the whatever. And then the mantissa is the 1, 2, 3, 4, the 1, 2, 3, 4 in 1.234. So neural networks have this really interesting characteristic, which is fairly unique among computations that have been popular to do, where it turns out that you don't need much mantissa to do a really good job with them. That is, if you only have like 3 bits, that's like all the number you really need, or 4 bits. If we set the exponent part aside, and we just talked about the mantissa. Well, when you do a calculation, most of the stuff is the mantissa. Like if you multiply 2 numbers, you add the exponents together, but then you have to actually multiply the mantissa parts together. So the calculation itself is more sensitive to the mantissa size than it is to the exponent size. So with this format, essentially what they're doing is they're saying, okay, say we have an array, and I'm going to represent all the numbers in that array with just 8-bit values. And what I'm going to do with the numbers in that array is the 8-bit values in that array, 4 of the bits are going to be for mantissa, and 4 will be for exponent for each one of the numbers in the array. And in addition to that, what I'm going to do is I'm going to have this other exponent that sets aside. It's called an exponent bias in the format document that Tesla created, which is just basically all the numbers have this additional exponent offset to them. And this is a good fit for neural networks because you frequently have these giant, you might have millions or tens of millions of numbers in an array, and they all fall into a relatively small range. So the small mantissa and small exponent is all the representational power you need within the array itself, except for the fact that they all have an exponent offset. And so that's like this other number that you set aside, which so your array has the elements of the array, and then you have this one scalar value that goes with the array that basically says, and this is an exponential offset for this whole array. And when you do math between these arrays, you just work with the values inside the array. And then, for instance, if you multiply two matrices, you just add the two exponents together, and all of the output values get that new exponent bias. So it's a really efficient and clever way of dealing with numbers where, if you consider all the different calculations you might do, you might need a relatively large dynamic range. You might need a lot of bits for your exponent. But for any individual calculation, you don't need very much. And because individual calculations in a neural network, an individual is an individual matrix multiplied by another individual matrix. That might be, a billion, individual calculations, or a trillion individual calculations. So it lets you, like, instead of having this computer where you're asking it to add the same number over and over and over again, kind of pointlessly as part of what it's doing, you just add that number once in the exponent, and you make a note of that. And then the rest of the calculation is just the stuff that actually matters in that part of the calculation that actually varies with this calculation from some other calculation. Does that make sense?
Yeah, generally. I mean, why do you need an offset?
So, imagine if I'm talking about the price of cans of soup, my offset is like $1 or a penny, right? And that's fine. If I'm talking about the cost of houses, I might be talking about hundreds of thousands of dollars or millions of dollars or something like that. In both cases, when I'm thinking about making a decision about whether I want to buy this house or whether I'm going to buy this can of soup, most people don't use 6 digits of precision, right? It's not, 1.234567 dollars for this can of soup, or when you buy a house, $123,456. You don't do that. The offset is just like, what's the category of number that I'm using? And so in neural networks, sometimes you're talking about houses and sometimes you're talking about cans of soup. But if I have a big bunch of cans of soup, I don't have to remember for every can of soup, oh yeah, this is designated in dollars as opposed to hundreds of thousands of dollars. I got a truckload of cans of soup and I just have this one number, which is their cans of soup. The price is in dollars and cents. And this other category, houses, it's like maybe the prices are in millions of dollars, right? There's a scale difference between the two.
Got it. So is the offset that Tesla is including, is that different for different categories of types of numbers? Yeah. Oh, okay.
So in a neural network, broadly speaking, you have activations, gradients, and weights that you're dealing with. And activations can be relatively large, and gradients and weights can be pretty small. So your calculator needs to be able to deal with all three kinds of numbers. And there's a lot of variation between, say, the scale of activations and the scale of gradients. But when you're dealing with a matrix that just contains gradient values, they're all the same scale. It's a very small scale. So instead of having to write the scale in every single number over and over again for an array that might have millions and millions of entries, I just have one notation, which is this is the scale of this matrix. And then the individual matrix values just take the number of bits that are necessary to differentiate them from each other.
Got it. Okay, so let's take a step back further. And you say to take advantage of these new numerical formats, custom designed hardware arithmetic units are required, so these benefits are not available to existing or future CPU, GPU, NPUs, which do not support them directly in their hardware designs. You say software emulation of calculation in these formats would be egregiously inefficient on existing hardware. So, and then your last tweet says, hey, this enables third parties to consider these formats for forthcoming hardware and software changes so as to enable future Dojo capability. So it seems like Tesla is, doing it for themselves, obviously for their Dojo, but
this
also—
is in the D1 chip, right? On AI Day, they told us these are the formats we're using in the D1 chip. So they're doing these calculations internally on the D1 chip. They're storing them that way. They're moving the numbers that move back and forth between D1 chips in an array are in these formats.
Mm-hmm. So then it seems like Tesla's broadcasting this, say, hey, if you want to be compatible with Dojo and how we're doing this is how you can make it compatible. But exactly who are these targets? Like who wants this information?
Who would they broadcast it to?
Yeah.
So anybody who wanted to build a piece of hardware that was going to interface with Dojo or write a piece of software that was going to be compatible with inputs and outputs from Dojo might want to be aware of these formats. So that's one potential audience for this paper. And the other potential is, say that you're another company, maybe a smaller company, or and you're building your own piece of hardware and you have the same problem that you're trying to solve. You want to build this piece of silicon and you want to just do neural networks with it, and you're thinking about your own 8-bit floating point format. Well, you could invent your own 8-bit floating point format, and it would be a little bit different. Maybe it would have some advantages or disadvantages. But one big disadvantage is that if you become successful and Tesla becomes successful, there's this barrier between moving data or having your systems interoperate, which is the numerical format being different. And that's a huge barrier. Relatively small differences in numerical format can make two pieces of hardware completely not interoperable. So if you're a company that is considering making your own numerical format, or maybe you're already making your own numerical format, you might look at it and say, well, hey, Tesla's building this big Dojo thing. It's an advantage to us to be compatible with that potentially at some point in the future. So instead of going our own way, maybe we'll tweak it a little and just use what Tesla uses. And also, there is some cleverness in what Tesla's doing. For instance, having this exponential offset, which is you maintain as a separate value, that kind of changes the way that you go about building a calculation engine to do this kind of stuff and build the hardware to do this kind of stuff. So, I wouldn't be surprised if there are people who read the paper who are working on a similar problem. Well, that's a clever idea. I think maybe we'll try that too, right? And all of a sudden now, both the hardware and the software that they develop is potentially interoperable with stuff that Tesla doesn't feature. I think Tesla putting this out there, advertising the format, is a way of getting more buy-in from more people. Because you could imagine the opposite thing. Like Tesla comes up with, they've got their 8-bit format, kind of like they did with their charger, for the car. They came up with this great charger. It's the most, it's a great charging cable or whatnot. But then the industry went a different way. So down the road, Tesla has this problem where, we have so many plugs and we built so many cars, but our cable is different from everybody else's cable. And that becomes, an impediment at a certain point. So this is a way to inform people what they're doing. And hopefully if the IEEE decides to make an 8-bit floating point standard, they would take this into consideration and maybe go this route, or at least try to do something which isn't pointlessly differentiated from this approach.
Interesting. So does Google with their TPU kind of, neural net training chips too, do they do anything like this? Do they have a separate numerical format, you think, or are they just using the standard?
So the history of numerical formats in neural networks is kind of interesting. But neural networks have not been the dog; they've been the tail. That is, nobody's built hardware specifically for doing neural networks, with a few exceptions. Google's TPU was one of those. But even when Google built their TPU, the first TPU was an accelerator that connected to another computer. So they needed to be able to move the data quickly from their accelerator to the other computer. So making up a numerical format, which is really hard to convert, like where, for instance, if you were to write a software conversion layer, it would take many, many clock cycles. That would make the accelerator a lot less useful, because you'd have to write all of these interchanges and you have to suffer the time conversion on that stuff. So Google kind of did this hack, which is actually pretty clever. So there's a 16-bit floating point format that the IEEE created, FP16, which is it's a reduction. Most scientific calculations get done in 64 or 32-bit floating point. The 16-bit floating point was sort of this hack that the IEEE did to just make something that was smaller for people who didn't need all of the power of a 32-bit floating point number. But it turned out that the trade-off between the mantissa and the exponent that they did for that was actually a really bad trade-off for neural networks. So Google did this thing where they just took a 32-bit float, which it turns out has a 24-bit mantissa and an 8-bit exponent, and they just took 16 bits of the mantissa, throw them away. So like in memory, it's a 32-bit value, and you just throw away 2 of the bytes, and you get this weird kind of chopped down 32-bit format, which is now 16 bits. And Google called it a BFP16. And it turned out that the mantissa exponent trade-off, and that was actually a much better fit for neural networks. So Google's been using this kind of hacked format, and it became popular enough that other people support it. In fact, Tesla supports that, non-IEEE, non-standard format in their FSD computer. And, NVIDIA's been adding it to their recent accelerators and whatnot, because even though it's a hack, it's seen as a useful way of dealing with the fact that, like, we don't want to be writing 32-bit numbers because it just wastes half our bandwidth. Like, if we only need the first 2 bytes, just throw the others away. Don't bother writing them to memory. Don't store them. Don't read them. And because, if I can do in 2 bytes what otherwise was taking me 4 bytes, and I'm talking about doing this, trillions of times, I've saved half my bandwidth. And that's this is where Dojo ends up with a 2x, 4x speed up. A very large number of the operations that they're going to be able to do with these CFP8 values, traditionally you would have had to do with a 32-bit floating point number. So that's a 4x reduction in storage, bandwidth, computation, power use, so forth.
Interesting. So yeah, I mean, so they're going from like a 32-bit down to 16 or 8, and that's the 2 to 4x improvements there. So does Tesla need to, do you think, rewrite much of their kind of code for training as they implement this new kind of numerical formats, or is it more just on the hardware side?
The conversions will be done in hardware. For some things, one of the things that made the Google BFP16 hack so clever was that it's a really trivial software, because, software can read 4 bytes and throw 2 of them away. And that's a very simple operation in a computer. But imagine that I'm reading 4 bytes, and I'm going to take these 7 bytes and put them here, and these bytes and put them here, and take one more bit and put it on the top. Well, now instead of being like one computer instruction or something I can do with DMA, it's several computer instructions. It's not very efficient. And that was kind of the problem that we had with these other numerical format conversions, is that in order to get a number well packed into numerical format, you have to do a lot of bit shifting and bit movement. And CPUs and GPUs are really bad at doing these bit level operations at that scale. So what you want is hardware to do that, because designing the circuit that does that in one clock just on the fly is actually a really easy thing to do, but you have to build the hardware to get it.
Interesting. So I want to go ahead and read you. Actually, I don't have Elon's tweet here. Elon, he replied to Tesla's announcement of this, saying like, this is more important than it seems. More
important than it seems,
or something along those lines. What do you take of that? How do you interpret his kind of comment there?
I think the way I took it is numerical formats, in this case, they matter. Like, they have a big impact on the performance of the hardware that you can build around them. And it's actually kind of surprising that we've gotten this far into the neural network. Like, I've been waiting for a couple of years for somebody to come up with a 8-bit floating point format, because it's so obviously the thing that somebody should do, and nobody did. Why? And I think the deal is, if you're NVIDIA, right? NVIDIA makes chips that sell into systems that have to operate with lots of other people's chips, and they have lots and lots of customers that have all this software. So when NVIDIA comes out with a new format, it's a lot of adaptation by a lot of other parties that they interact with. In a sense, it's easier for Tesla with Dojo to go their own route, because at least on the first cut, they're writing all the software and they're designing all the hardware that interfaces directly. So they can pick something that's ideal for their purposes. And at a first cut, because they're building everything, they don't have a lot of people who have to adapt software or hardware to work with their format. And I think that's why Intel, NVIDIA, AMD, they haven't gone out and done this format, because they want the IEEE to do it, or they want to get together with 5 other manufacturers and agree on a standard before they move forward. And that just hasn't happened.
Do you think in order for Tesla to release this new, let's say, numerical format, the 8-bit floating point, is it a requirement for them to like make their own chips? Is that how this comes about? Like, as they're creating Dojo, they have to decide on a numerical format, and so they say, hey, we have this better, more efficient way to do it, therefore we release the standard. But if they're not going to create their own chips, if they're still using NVIDIA chips, then is there any really reason, or is there any path for them to create their own numerical format standard?
I guess you can think of it coming from two directions. Like if you're not going to build your own software, if you're not building your own hardware, you're stuck with the numerical formats that are implemented in the hardware that you're using. So, if you buy one of NVIDIA's GPUs, they have a half dozen or a dozen numerical formats they support. And for you to use any numerical format other than those is going to make your software just unbelievably slow. So you're not going to do that. You're going to use one of their formats. The flip side is if you're building your own hardware, well, now you're free to pick any format you want, because the numerical format is a hardware constraint. If you build the hardware, it's not a constraint to you. But once you build the hardware, it's a constraint on all the software that runs on that hardware.
Mm-hmm. Okay, got it. That's interesting. So, I mean, I'm just thinking of it conceptually, like on a higher level. Like, it seems like from what I'm getting from this conversation, this numerical format change, in and of by itself, it really can drastically improve performance, because you're removing the numbers or that the system doesn't need and bringing them down to exactly what they need. So, like, for example, if they hypothetically, which they couldn't, if they enacted this new numerical format on NVIDIA hardware, which obviously they're not able to, would it have that type of 2 to 4x performance improvements? You think? Really?
No, it would be really smart for NVIDIA to implement this right now that somebody has done it.
Yeah.
I mean, normally what NVIDIA would do is they would wait for somebody else. I mean, for instance, NVIDIA supports the BFP16 format. Google built it. Google started building it into their TPUs. And, people do run code that runs on NVIDIA GPUs, and that interfaces with code that runs on TPUs. So for them to support it in hardware, it kind of makes sense. It makes things, but it also makes sense because running BFP16s natively on the hardware on your GPU, it's a better fit for the calculation itself. So there's less. It makes your software simpler for the results that you get, I guess is a way to say it. So they had FP16 support NVIDIA had that before they had BFP16 support. Mm-hmm. When they added BFP16 support, well, BFP16 was just obviously the better choice. Like if you have a piece of hardware, if you're writing a neural network, training system, and you have a chip that can support FP16 and BFP16, it's no contest. Use the BFP16, right? But NVIDIA didn't see their way to supporting it until somebody else had already done it.
Got it. I mean, do you think Tesla is using the BFP16 format for their NVIDIA GPUs right now? They are?
No. On their NVIDIA GPU?
Yeah.
Yes. They're almost certainly doing it. Like if you're doing training on NVIDIA GPUs right now, and the version of the NVIDIA GPU you have is recent enough that it has BFP16 support, you're probably using it. You will end up using a hybrid of 32-bit and 16-bit for technical reasons that I won't get into. You won't strictly use the BFP16 format, but you'll mostly, like 99.99% of your calculations will be in the BFP16 format.
Okay, got it. All right, James, interesting, fascinating stuff. Is there any kind of final, take a step back, really high-level implications that you're taking from this whole announcement, this white paper of numerical formats? I mean, does it show Tesla, progressing on being really serious about, Dojo, their training platform? Is this kind of something that you'd expect Tesla to do? Is there any other kind of high level maybe takeaways?
It's more in the vein of things we've talked about before. Tesla is building their own hardware, and so this is something they can do. It's clearly something that should be done, and they did it because they can do it and they should do it, so they did it. There are people who don't do that because, like NVIDIA didn't do their own format for a while. Now, NVIDIA has different constraints. They sell a product into a customer base and so on. NVIDIA isn't building these chips just for their own internal consumption, right? When Google first started doing BFP16 on the TPUs, that was just internal consumption, which is a big part of why they could get away with it. They didn't have to comply with, they knew all the applications that the chip was going to go into, and they knew the consequences of adding this format and how to do the trade-offs and whatnot to make that work. So Tesla's both in a position to do it, and they're also they have the kind of institutional character, which is like, if this is a better way to do it, this is the way that we're going to do it. And there may be complications, but we'll sort them out down the road. And we don't need anybody else's permission, and we don't need to enter a standards group because we want to go fast. We're just going to do it. A lot of other companies would have done a thing, where like if Intel had wanted to do this, Intel would have got 2 or 3 other chip makers together. They would have started a standards committee at the IEEE. This is the way these things are normally done. This is how the other floating point formats are created. You get a bunch of players together who individually don't want to commit to doing something that might be incompatible with what the others do down the road. You form a nominally neutral committee at the IEEE to hash out the differences. They publish a standard, and then everybody builds their hardware according to that standard because it's safe. It's very safe, but it's slow. Committees are slow. They take a long time to like come up with a solution. And Tesla's not going to do the committee thing. They're just like, this is the right way to do it. We're just going to do it. And now that they've done it, hopefully we will see a lot of other people just jump on this and use it, because it would be great if NVIDIA would support this. Like, it would definitely make NVIDIA's GPUs much better at doing neural network training if they would just support this format.
Great. One last question here is, when do you think Dojo is going to be up and running to the point where it's going to actually have an impact on FSD?
Yeah, so my experience with estimating these kinds of schedules is with normal companies, and Tesla's not a normal company. Like, I keep being surprised that wow, they're already there. So I think last time we talked about this, I said, well, if it was a normal company, I'd say a year or two. But AI Day was 6 months ago. Maybe they've already got a room full of these things running it because it's Tesla. I don't know. Yeah. Normally it's like a couple of years between the time that like you get the first thing running on the desktop and you've got, something running at scale, at the kind of scale where it actually is offloading this supercomputer you have in the back room. I have a really hard time imagining making that happen in less than 6 months, but then they surprise me. So maybe they have it now. Maybe they won't have it for 6 months.
Yeah.
But
got it. Awesome.
Yeah, if it was IBM, they wouldn't have it for 3 years. So that's the
fantastic. Yeah, this is actually super helpful for me to understand the Dojo Whitepaper, the new numerical formats, and just what Tesla's doing behind the scenes. Would love to have you on as soon as possible to discuss more AI topics. This is always fascinating. I think this is like one of the foundations for the next decade to understand where AI is headed. Has so much impact on so many things. But thanks, James. And we'll talk again.
Great chatting with you.
All right. See ya.